Well, the good news is you get tonight off. You have no calculus in your homework, but you do have to do a pre-calc review homework. So we're going to review inverse trig functions, and it's important that you remember this because in our next lesson then we'll find the derivatives of the arcsine, cosine, and arctangent functions. So remember that an inverse function must be 1-to-1. So it must pass the vertical line test and the horizontal line test. No x's can be repeated. No y's can be repeated. So when you make your graph, it would be very helpful if you made your units square. So if I use the space available here for pi and 2 pi, keep in mind that that value of pi is approximately 3 units. So you are going to find your graphs of inverse sine and cosine much easier if you try to square up your graph. Doesn't have to be perfect, but I think our tendency is to make a sine or cosine wave much taller than it actually is on a square graph. So our sine wave at 0 radians, at pi over 2 we're at 1, at pi we're back to 0, at 3/2 pi back to -1, and at 2 pi we're back to 0. And of course the same pattern would repeat at negative pi over 2 and at pi. So let's graph our sine wave. And you could be more accurate if you used some graph paper. So here we've got negative pi over 2 and positive pi over 2. So our sine wave, of course, is a periodic function that would continue. So the entire sine wave desperately fails the horizontal line test. So how do we choose a section of this graph that passes the horizontal line test? We would have to choose a restriction so that a horizontal line never passes through the graph twice, which means we want to restrict our graph to a 1-to-1 section. You can't go through any valleys or over any hills. So think of a minimum height to a maximum height, and we might as well choose that value as close as we can to the origin. So if we restrict the graph to this region from negative pi over 2 to positive pi over 2, then the next thing that's helpful, I believe, for most students in graphing the inverse, remember that it is going to be the reflection over the 45-degree line y equals x. So folding it across that 45-degree line, and again I have a little bit of a problem here in that I'm not using graph paper, so this should actually be a little sharper for this y equals x line. All right, if we think about our ordered pairs on our graph, here we've got pi over 2 comma 1, and here we've got negative pi over 2 comma -1. So now when we do our inverse, we know that the x's and the y's trade places. So the endpoint pi over 2 comma 1 is now going to be at 1 comma pi over 2. And the endpoint on the negative pi over 2 -1 is going to be at -1 comma negative pi over 2. So it's very helpful if you remember that you're folding across that 45-degree line. So negative pi over 2. So the 0, 0 point, of course, stays on the reflection line. And then you want to visualize folding this graph across the 45-degree line. And there is our graph of arcsine or inverse sine. So we want to remember that we're restricted to quadrant 4 through quadrant 1. All right, let's try cosine, the same idea. And if I use the space that's available here for 2 pi, then if I did that same idea here, counting off units on our graph, and again, it doesn't have to be perfect here for our units, but our cosine wave, remember, starts at 1 and then at pi over 2 it's 0, and then at pi it is at -1, and then back to 0, and at 2 pi we're back at +1. So our periodic graph that we could continue, I think my point is shifted over a little bit there. So we could continue this graph. And now we want to think about what section of our y equals cosine graph passes both the horizontal and the vertical line test. And we want to make sure we don't go over any hills or through any valleys and stay as close to the origin as possible. So this section of the graph, and mine doesn't look real symmetrical here, not using graph paper, but this section of the graph from 0 to pi looks like a section that would pass the vertical line test and the horizontal line test. Of course, we could have chosen a section on the other side of the y-axis, but it seems much simpler to choose those positive coordinates. So again, let's use this hint of labeling our endpoints. So here we're at pi comma -1. This intercept point is at pi over 2 comma 0, and of course the y-intercept was at 0, 1. So now let's use that same trick we did a minute ago. We know that these points will trade places, so we'll be at 1, 0, and then at 0 pi over 2. And this is where I was suggesting that you keep in mind that pi over 2 is a little bit more than 1.5. And our point at -1 positive pi. So that point is over here, -1 positive pi. And now can you picture folding across the y equals x line? So we want to get our concavity correct here. So this is the basic shape of y equals inverse cosine. So keep in mind that you were starting with quadrant 1 through 2 on the unit circle, I think is the easiest way for me to think about that. The tangent function, I think, is easiest for arctan because it's obvious that we only want to draw one section of the tangent graph. So we want to go from -pi over 2 to +pi over 2, just as we did for sine. So notice that tangent is undefined at -pi over 2 and at +pi over 2, and of course again at 3/2 pi and so on. In quadrant 1, we know all functions, all 6 trig ratios are positive. So remember that here we're in quadrant 1. So that's how you know that it rises between 0 and pi over 2. All 6 functions have to be positive between 0 and pi over 2. So there's one branch of our tangent curve. And we could, of course, repeat. We know that there will be additional branches of our tangent curve. But for our inverse problem, of course, we wanted to restrict it to just one section that is 1 to 1. And now when we fold across our 45-degree line, I think this is much easier for students to visualize because of that analogy that looks a little bit similar, the cube root of x and x cubed. But now remember that this is not quite the same because the graph of the cube root of x rises infinitely, as opposed to inverse tangent has asymptotes. So what used to be a vertical asymptote is now a horizontal asymptote. Can you picture folding this graph on this y equals x 45-degree line and seeing that the blue function would be the reflection image of the red? All right, so for domain and range of each of these functions, so remember that the range of the inverse function comes from the domain of the original. So we have to be careful about domain and range. So the range that we end up with was the restriction in the domain of the original. So for our range for sine, we went from -pi over 2 to +pi over 2. In other words, I like to think of this as quadrants 4 through 1. Quadrants 4 through quadrant 1. And for arc cosine, we restricted it to 0 to pi. That's the top semicircle. Let me make these closed endpoints. So I like to think of this as quadrants 1 and 2 from the unit circle. And for arctangent, it's the same as it was for sine. Think of where the asymptotes are. Don't try to memorize these. You know these graphs well enough. So you want to think of quadrant 4 through quadrant 1 again. So our domains then go from -1 to +1. They're because we flip-flopped the x and the y coordinates. For arctangent, remember our domain then goes from -infinity to infinity. So quite a bit different. All right, so you have space on the backside of the worksheet to try that again on your own. So definitely worth it. Pause the video and do those problems again to make sure that you understand. All right, simplification. When you see an arcsine problem, you simply have to remember that it's an inverse. So I'm giving you the answer of -1/2. You have to say what angle has that value. So a sine of -1/2 means that the y-coordinate was -1/2. And you know in our special triangles that's a short 30, 60, 90. So that angle is -pi/6, and it is between our restriction of -pi/2 to +pi/2. So an arctangent problem, when you see this 1 over the square root of 3, I hope everyone will recognize where that must have come from the legs of a 30, 60, 90, where we had the short leg to the long leg. And remember, our definition of tangent is y over x. So in other words, the vertical leg is the short leg, and the long leg is the x-coordinate. So I hope you can picture where that would come from, where we have the short leg is the y-coordinate, the long leg is the x-coordinate. So the halves would cancel out whenever we do this. So if you have the square root of 3 in the denominator, you know that the long leg was with the x-coordinate. So I hope you're still not making tough work of those special triangles. And in G, now we have the arcsine of a sine. And I hope your first intuition is to say, well, an inverse sine of a sine has to cancel out, and we should get right back to 5/6 pi. But there's a wrinkle, of course. 5/6 pi is over here in quadrant 2. And we are not allowed to give an answer of 5/6 pi. So while we want to think this would cancel out and give us right back to this angle, that's not true. So the easy answer, however, we have to stay in quadrant. Remember, arcsine has to be between -pi/2 and +pi/2. So we want to just think of the same triangle with a positive sign. So we want to think of its reflection image, pi/6. All right, let's do that a different way here in case you lost that. Let's do this inner parenthesis first. What is the sine of 5/6 pi? That would be +1/2. And then you would say, now what is the arcsine of 1/2? And now you can see why we get back to the angle that has a sine of 1/2 would be pi/6. All right. And we have a similar situation in, if I don't scroll too far, in H, where we're doing arc cosine of a cosine. So again, I hope your first instinct is to say they must cancel each other out, but this is not in the restricted region. Remember, for cosine that we are restricted to 0 to pi, the quadrant 1 and 2. So think what we're asked to do here. We're looking for an angle, or we're looking for the inverse cosine of -pi/4. And you can see our problem. -pi/4 is down here in the wrong quadrant. But we are doing an inverse cosine, so we want to say, well, isn't there another triangle that has the same cosine? And that is its reflection image right up here in quadrant 1. So instead of -pi/4, we do its reflection image and choose +pi/4. Again, if you didn't like that method, then let's do step-by-step process. When you do the cosine of negative pi over 4, you would get 1 over the square root of 2, or if you rationalized it, square root of 2 over 2. And then you want to say what angle has that cosine. And when you do an arc cosine, you know that you're restricted to the upper semicircle, so you would come up with pi over 4. All right, so on the back side, you're going to do some practice of the same problems, and you can come right back. You can pause the video if you want to check your graphs. So pause the video now to do 1, 2, and 3. And then let me just scroll here so you see each one again. This is just repetition to make sure you've got it. There's graph number 2. And you can pause the video if you need to check that longer. And let's see if I can scroll to graph 3. And it's very important that you remember those restrictions. All right, so try these bottom problems before you use the video to check your answers. And it's fine if it takes you, if it helps you to think of a drawing. When you do an arc cosine of 1/2, you're saying what angle has a cosine of positive 1/2. And I hope without too much effort you come up with that tall 30, 60, 90. What angle has a tangent of -1? And remember, for arc tangent that you're restricted to quadrant 4 through quadrant 1. So you know you want to do a 45, 45, not a great triangle. So we know that we want to do negative pi over 4. So make sure you don't say 7/4 pi, because that's outside the restriction from negative pi over 2 to positive pi over 2. So arc sine, what angle has a sine that is negative square root of 3 over 2? That's our tall triangle in quadrant 4, so we want to stick with negative pi over 3 to be within our restriction. And inverse tangent, remember that these come from the 1/2s canceling out. So it's the long leg for the y, long to short, and tangent is y to x. So we know that this is the tall 30, 60, 90 to get a tangent of square root of 3. The tangent is bigger than 1 when the triangle's vertical leg is longer than its horizontal leg. So again, think of those long and short analogies. All right, so a couple different ways of doing this sine of an arc sine. There we don't have to worry about the restrictions. We know we'll come right back to this. So that will cancel out. Let's do it step by step. If we do arc sine of negative square root of 2 over 2, that would give us a negative pi over 4 angle. And then, of course, you would see the futility, because now you want to do the sine of that angle. So, of course, you'll get right back where you came from. So sine of an arc sine, there's no problem with the restriction. Here's where the restrictions can come in, though, in the remaining problems. So if we're doing inverse tangent of the tangent of 0, well, the tangent of 0 is 0. So where does that happen? The tangent is equal to 0 at 0. Sorry. I switched windows there. Hopefully you see the tangent, arc tangent of 0. And for question 10, now we want to be careful about our restrictions when we have the inverse on the outside. The inverse of the cosine almost cancels out, but negative 3/4 pi is outside of our restriction. So negative 3/4 pi would be this angle. So we want to choose its mirror image that is within the restriction. So we want to come up with positive 3/4 pi. And number 11, we want to do the inverse cosine of the sine of negative pi over 3. So we guess we have to think this through here. The sine of negative pi over 3 is negative square root of 3 over 2. And now we want to say what angle has that as its cosine. And cosine is negative over here in quadrant 2. So for our cosine, we're restricted to quadrants 1 and 2. So this would be our 5/6 pi. And just two more. Number 12, similar problem, but now we're doing the sine of negative pi over 6 is negative 1/2. And now we want to say what angle has that as its cosine. And cosine of negative 1/2, but remember we have to stay in quadrant 1 and 2. So negative 1/2 is the angle 2/3 pi for cosine. And in number 13, again, could be a restriction problem. These might not cancel out. They should almost cancel out, however, but we're outside our restrictions. So again, the cosine of negative pi over 3, this angle doesn't work for us, but it has a cosine of positive 1/2. So the same angle in quadrant 1. So we want to just do a reflection image to stay within our restricted units.